Infinite numerical integer series. The secret of the 85-digit cubic quadruple. My motto: plain honesty, simple truth, easy understanding. The joy of finding things out for yourself. A cubic quadruple is an equation of the form d cubed equals a cubed plus b cubed plus c cubed. For example, 9 cubed equals 8 cubed plus 6 cubed plus 1 cubed. On his power page, retired university professor Stephen Dutch, formerly of the University of Wisconsin, Green Bay, gives 16 cubic quadruples with smallest term plus 1. Here are 7 of them. He then goes on to say, the list above resulted from a search where B and C ranged up to 10,000, so it appears the cutoff at B equals 2676 is a real limit. These are almost exception to Fermat's last theorem. Since cubes can be negative, we also find this set of almost exception to Fermat's last theorem. Again, since the search ran to B equals C equals 10,000, the cutoff at 3753 is probably the real limit. He was absolutely wrong. As you can see, on the 27th of January 2010, I came up with the infinite series shown of cubic quadruples that end with +1, where we calculate the base numbers d and a from the two formulas and c equals 1 always, and b is the consequence of the other three, and using the computer algorithm for n equals 1 to infinity, we get an infinite sequence. The first 5 quadruples are those that were highlighted blue in Stephen Dutch's first table. In the following month, from the Euler-free website, I found the following algebraic equations for the cubics for both +1 and -1. The first 5 negative cubic quadruples generated were those highlighted blue in Stephen Dutch's second table. By equating comparable quadruples from both series, where two terms are identical, we generate a third infinite series, where the last two base numbers always have a constant difference of 2. The quadruples produced when a is odd are composite and divide by 2, so the last two terms always have a difference of 1. So we end up with 2 as opposed to 1 infinite series, one when a is odd and the other when a is even. 4 for the price of 3. In a comment he makes about Fermat's last theorem, Stephen Dutch says, the possibility that there might be a simple solution to a famous problem attracted cranks by the score. Why exactly cranks think they will become famous by solving famous problems is a mystery. How many mathematicians have megabook endorsement contracts? Well, for this crank, who discovered what he failed to discover, it's not about fame or fortune, but integrity and honesty in mathematics, which I find is sadly lacking. Why do we have positive and negative cubic quadruples? Yet, when he discusses Pythagorean quartets, that is quadruples, Professor Dutch, like mathematicians generally, only cover positive ones, and not 20 squared equals 16 squared plus 15 squared minus 9 squared, of which the Fibonacci identity would generate infinitely many. This crank also knows several easy proofs of Fermat's last theorem, so here for the benefit of the intellectual elitists is one of them. Take 3 integers z greater than y greater than x. Form the Fermat equation. Multiply through the Fermat equation by the composite zyx to the power n. Form 3 coefficients. k1 equals yx to the n, k2 equals zx to the n, k3 equals zy to the n, where k1 less than k2 less than k3, and let z equals z to the n, y equals y to the n, and x equals x to the n. Then k1 z squared is equal to k2 y squared plus k3 x squared. A contradiction, because it contravenes the distributive law of multiplication for the powers, QED. Furthermore, 20 squared equals 16 squared plus 15 squared minus 9 squared is just 4 squared 5 squared equals 4 squared 4 squared plus 5 squared 3 squared minus 3 squared 3 squared, obtained along with two other positive quadruples by multiplying through the triple 5 squared equals 4 squared plus 3 squared by each base number to give the following three equations, and making the substitutions as shown by the colours. Only Pythagorean triples produce these quadruples. Expressing the equations algebraically, then the exponent becomes an n, so it applies without exception to any Fermat equation that might exist. Hence, the Fermat equation is a contradiction, since it has been demonstrated that numerically for an all-integer solution, only Pythagorean triples produce Fermat-Bateman quadruples. So the secret of the 85-digit quadruple was to select an appropriate integer, feed it into the equations I have just revealed to get the required base numbers, and voila, the 85-digit quadruple. End of video.